All right, so in this video, we're going to be looking at the domain and range of trigonometric functions and their inverses. So we are dealing with 6 standard trig functions: sine, cosine, tangent, cotangent, secant, and cosecant, and their inverse functions. We have different notations for them. So inverse sine or arcsine, inverse cosine or arccosine, inverse tangent or arctangent, inverse cotangent or arccotangent, inverse secant or arcsecant, and inverse cosecant or arccosecant. Now, the cosecant and the cotangent functions are used the least, but they basically work identically to the secant and tangent functions. Same thing for their inverses. So we are going to gloss over them somewhat because they basically follow the same rules. We will talk a little bit about their asymptotes being, for instance, or their domains being in slightly different places because of where the asymptotes are in the originals. But fundamentally, if you keep those slight differences in mind, then you'll be able to work with them basically by just keeping those similarities straight. So let's start with the sine. The sine graphs are shown below in different scales, but basically the domain of the sine function is all real numbers. You can do this wavy sinusoidal function forever in either direction. The range, though, is only from -1 to 1. Now, one issue that we have to deal with is the fact that this is not a 1-to-1 function. So when we go to look at the inverses, we're going to have to take that into account and restrict the domain to a section of the graph where we can get all the possible values of the sine range without having to deal with repeated values. Now, because the domain and range the domain in particular is -infinity to infinity, if we do any horizontal transformations on the sine function, any stretching or compressing, any scaling of any sort, or any horizontal shifting, that does not in any way affect the domain of the sine function. Sine functions will always have a domain of -infinity to infinity. The range of the sine function is not altered by horizontal shifts, but if you apply anything outside the sine function, then that will affect your range. So if I multiply the sine function by a value, I will multiply the range by that same value. And if I add anything to the sine function on the outside, that will also affect the range that I'm able to obtain. So I would get -a plus b and all the way up to a plus b. So for instance, the graph of 4 sine x plus 3 has a range of -1 to 7 because this is -1 times 4 plus 3 gives me -1, and +4 plus 3 gives me 7. So this is a picture of that graph. And again, if you graph it, you can see this starts at -1, and it actually, if this is 10 up here, this is 7 right there. Now, if we look at the inverse sine function, then as I noted, the domain has to be restricted to a section of the graph where we go through the entire range of the original sine function. And the place where we do that is between -π/2 and π/2. So in this section of the graph, it is a 1-to-1 function, but that we have to restrict the domain to just this section. So if this domain of the original sine function restricted, this will become the range of the inverse sine. And then the range of the original sine function in this section will become the domain of the inverse sine function. So the inverse sine will have a domain of -1 to 1, and the range will only be from -π/2 to π/2. It is not -infinity to infinity. This is a very common mistake but we have to restrict the domain in order to get the inverse at all. Otherwise, it's not a function. Now, because of that, any horizontal transformations are going to affect our range for our inverse function. So any of those transformations would have to be applied. So if I'm doing sine of 2x plus pi, I have a horizontal compression factor. That's going to give me the range is going to shrink from negative pi over 2 to pi over 2 to negative pi over 4 to positive pi over 4. And then I'm going to shift it by leftward shift of pi over 2 because I have to factor this 2 out. Remember, so this is 2 times x plus pi over 2 is my horizontal shift. And then therefore, since this is a leftward shift, I'm going to subtract pi over 2 from each of these endpoints. And that's going to give me negative 3 pi over 4 to negative pi over 4. So that's my graph. Again, that's the restricted graph of the original function, where I have, again, that string of values for the sine function that goes from here to here. And then again, similarly, we would do transformations on the domain of the inverse sine function in the similar way that we would transformations on the range of the original sine function. So for the cosine function, this is going to work very much like the sine function, except there is a shift of pi over 2. So the domain that we're going to be looking at when we restrict the graph is going to go from 0 to pi, rather than from negative pi over 2 to pi over 2. But this is essentially a leftward shift of pi over 2, and you get back to the original sine graph. So for the regular cosine function, the domain is all real numbers, but you can't use that when you go and you do the inverse cosine because the original function is not 1-to-1. So we restrict the domain and therefore the range of the inverse to be from 0 to pi. The range is the same. It's negative 1-to-1. And if you apply any transformations, any vertical transformations, then those affect the range in the same way that they affected the sine. And again, other than this range of the inverse cosine being restricted to 0 to pi, the domain of the inverse cosine follows the range of the original cosine. So again, transformations they only affect the range of the cosine, but they affect both directions in the domain and range of the inverse. So to find the domain and range of the inverse, we restrict the original function to 0 to pi, and then we apply our transformations to the domain to get the range of the outcome. So here, the restricted domain of the original is the range of the inverse, and then we apply our transformation. So this would go from 0 to pi, and then I have to add my 2/3 because remember, when I do a transformation like this, the horizontal shift is not just the constant. I have to factor out that 3. So the shift is actually 2/3. So I end up with the range of the inverse being from 2/3 to pi plus 2/3. And then the range of the original is equal to the domain of the inverse. And so those vertical shifts on the original function, the 2 and the 1, get applied to my original interval of negative 1-to-1, and I end up with negative 1-to-3. So here I have an arc cosine example and not just the original cosine function. And so the vertical transformations apply to the range. And then the horizontal ones apply to the domain. So, but the domain starts out as -1 to 1. And so if I'm shifting that by 3, I add 3 in both directions, and I end up with 2 to 4. In the case of the domain, I start out with 0 to pi, right? And then I apply my 1/2, and I add my pi over 2, and I end up with pi over 2 to pi. Now, the tangent function, like all of the other functions we're going to talk about, the secant, the cosecant, the cotangent, these have asymptotes. And the asymptotes are going to essentially be the bounds on our limitations for our inverses. So, for instance, tangent has asymptotes at -pi over 2 to pi over 2. So when we go to the inverse, that will be the restricted range of our function, the restricted domain of the original in order to get the range of the new function of the inverse. And the range is going to be all real numbers. So unlike the sine and the cosine, where transformations don't affect the horizontal transformations don't affect the domain, here horizontal transformations will affect the domain, but they won't affect the range because it's the range that is all real numbers. So typically our domain is of the form odd multiple of pi to odd multiple of pi. And in between there, we're good, but those odd multiples of pi are not good. If k is equal to 1, then, or k is equal to 0 here, then we have our -pi over 2 to pi over 2 original section of our domain. Now, when we do the inverse again, then this will become the range, and all real numbers will become the domain. So here's our transformation. We want to find the domain of this. We're going to have to apply our transformations to that original domain. So here, this is the generic case. We would take our 2k minus 1 times pi over 4 minus, it's over 4 because we're compressing it by a factor of 2. And then again, we factor out the 2 to get our horizontal shift. And then we apply that to this one as well. And we get this expression. If we set k equal to 0 to get that main interval where that one that was originally in the center has gone, it's here. It's from -3 pi over 8 to pi over 8. But the range is always all real numbers. So the 4 and the -1 here affect where our intercepts are, but they don't actually affect the actual result of that range. Now, to do the inverse tangent, of course, the domain is now all real numbers, and the range is the -pi over 2 to pi over 2. And so now this one has horizontal asymptotes instead of vertical asymptotes. And then we again make similar transformations in order to get our domain and range for the inverse. Now, cotangent is not normally found in your calculators. So to see this, you have to graph using one of the available functions. So typically, you can use 1 over tangent, or you can use cosine over sine. And that will also get you a graph. You can also do it as a transformation of the tangent. So it would be a vertical reflection and also a shift by pi over 2, either way. But the domain for these functions typically have, because of the cosine is 0, or sine is 0 at 0, and that's in the denominator, you get asymptotes at multiples of pi. So 0 to pi, for instance, would be this first cycle right here. as with the tangent function, the range is all real numbers. So again, we have similar issues when we deal with the inverse cotangent that we had with the regular tangent. What we would have to do is we would start with our domain of the inverse cotangent is just all real numbers. But then we would have the, by definition, the interval would be from 0 to pi for our restricted section of the graph. However, if you're going to plot this on a calculator, you can't actually, there is no inverse cotangent function on a typical calculator. So you would plot this as arctangent of 1 over x, and that will not give you values in between the interval of 0 to pi. It'll give you values on the arctangent range, which is not exactly right. So you do have to be a little bit careful when graphing any of these inverse cotangent, inverse secant, or inverse cosecant functions, because you have to use ones that are available, and the domain and range won't always match up, particularly for the inverse cotangent. Now for the secant, it's going to have the same domain and range as the tangent, because both of those functions have cosine in the denominator. Now secant is going to go, it's going to go to positive infinity, and it's going to go to negative infinity, but there is a gap between 0 and between -1 and 1. So the graph, the range is not all real numbers. The range is going to be from negative infinity to -1, and then from 1 to infinity. And in this case, in order to get the domain, we're going to have to split this graph around the asymptote, actually. We're going to have to split this from 0 to pi in order to get the full range of values at least one time. So it's still going to have the whole at pi over 2 in the middle of the domain. So mostly it's going to look like flipping the cosine function on that restricted 0 to pi interval, but it's actually going to be 0 to pi over 2, skipping pi over 2, and then going from 0 to pi. So because of that asymptote that's in the middle. And because of that, we're going to have to, if we have transformations on the secant function, then we're going to have to apply those both to the range and then also the restricted domain if we're doing the inverse function. But again, you're going to, if you're trying to graph the inverse secant function, you're going to have to use the arc cosine or the inverse cosine of 1 over the argument in order to get it. And so you'll get this graph. And again, notice there is an asymptote in the middle here. We don't actually use arc secant that much in regular trigonometry, but we will use it more in calculus for other reasons. But we don't have to graph it in those cases. We use it for a lot for trig substitution, honestly, which is a way of getting around some of the algebra for complicated calculus problems. And then finally, cosecant. Again, if you're trying to graph it, you would have to graph it as the reciprocal of the sine function. The domain is going to be the same as for the cotangent, because cotangent is cosine over sine, so that sine is in the denominator. And for secant and cosecant, they have the same range, again, for exactly the same reasons. As you get to 0, you go to an asymptote, but you don't actually get anything in between 0 and 1 because sine and cosine don't go above 1, so you can't get any of those fractions. And consequently, you do your transformations on the restricted range of the graph in the same way that we would for cosecant. And again, if we tried to graph this, The only way that we can graph it is not because there's no inverse cosecant on our calculators. We would have to graph this as arcsine of 1 over x.